In the silent depths of the cosmos, there exists a type of star so elusive that astronomers can count the known ones on their fingers, yet so powerful that each one could light up entire regions of a galaxy. They are the kind of stars that don't quietly pass through the universe. They roar, flare, and shed their very skins into the void, leaving clouds of golden fire adrift in space. If the night sky were a stage, these stars would not simply perform. They would set the stage ablaze, then vanish in a thunderous finale before the audience even knew the show had begun. These are the yellow hypergiants, rare, unstable titans that live their lives as if the clock is always running out. Every moment they burn is a battle against their own chaotic nature. Their existence, a delicate balance between expansion and collapse. They are not the familiar crimson giants that most skywatchers know, nor the searing blue beacons that dominate star-forming regions. They exist in the in-between, a brief, volatile transition that few stars ever occupy. And because of that, they have become some of the most mysterious and fascinating objects in all of astrophysics. For those who study them, yellow hypergiants are cosmic paradoxes. They are both massive and fragile, brilliant and unstable, rare and yet essential to the cycle of matter in the universe. When you peer into their golden glow, you're not just looking at a star, you're looking at a ticking clock, counting down to one of the most violent ends a star can meet. They are nature's fleeting masterpieces, painted in light and fire, destined to disappear before the universe has time to fully appreciate them. A yellow hypergiant is not just a bigger, brighter version of the Sun. It's a completely different creature. If our Sun is like a steady campfire, a yellow hypergiant is a raging bonfire the size of a solar system, with flames so intense they could be seen from across the galaxy. These stars are among the most massive ever formed, often tens of times heavier than our Sun, and their sheer size means they burn through their fuel at an incredible rate. They sit in a very specific place in the life cycle of a massive star, a point where the star's surface temperature is warm enough to give off a golden hue, but still blisteringly hot, thousands of degrees hotter than anything we could imagine on Earth. This golden color isn't just pretty, it's a sign of the star's balance, or rather, its struggle to stay in balance. It's caught between the blue-white heat of its earlier youth and the cooler red of its older age, and that in-between stage is incredibly unstable. From a physics standpoint, they are swollen to such a vast size that their outer layers are barely held by gravity. Imagine a balloon inflated so much that it trembles, with gas constantly streaming away into space. This is what life is like for a yellow hypergiant. Their immense energy output pushes against their own gravity, almost tearing themselves apart from the inside. This instability is why they don't remain yellow hypergiants for long, just a blink of an eye in cosmic time, maybe a few tens of thousands of years at most. To someone looking through a powerful telescope, a yellow hypergiant would appear as a brilliant golden white beacon surrounded by delicate clouds of gas and dust it has already shed. It would stand out in the darkness like a lighthouse made of pure plasma. But that view is rare, because these stars are scattered sparsely across our galaxy, and because their brief lifetimes mean they're hard to catch in this stage. In essence, a yellow hypergiant is a massive, luminous, and unstable star that exists in a fleeting phase of its evolution, too heavy and energetic to remain stable, too bright to go unnoticed, and too rare to be anything but extraordinary. It's the cosmic equivalent of a candle burning at both ends, brilliant while it lasts, but doomed to burn out far sooner than calmer stars like our Sun. In a galaxy as vast as the Milky Way, with its hundreds of billions of stars, you might think that every kind of star exists in abundance somewhere. But yellow hypergiants are so rare that even if you searched every corner of our galaxy, you could count the known ones on your hands and still have fingers left over. Astronomers estimate that, at any given time, there may only be a dozen or so true yellow hypergiants scattered throughout the Milky Way. That's not just rare, it's vanishingly rare. To put this into perspective, imagine walking into a massive stadium filled with 100,000 people, each person representing a star. In this crowd, almost everyone would be an average star like our Sun. Thousands would be red giants, a handful would be blue supergiants, but only one, maybe two, would be a yellow hypergiant. That's how scarce they are in the stellar population. Part of the reason for this rarity is their incredibly short lifespan in this phase. Stars can live for billions of years, but the yellow hypergiant stage may last less than 50,000 years. In cosmic terms, that's practically instantaneous. It's like trying to spot a single firework in the night sky when it flares for only a second before fading. You need to be looking at just the right place, at just the right time, to see it. Adding to the challenge, yellow hypergiants aren't all in one neat location. They're scattered across spiral arms and stellar nurseries, often hidden behind thick curtains of interstellar dust that block much of their light from reaching us. Sometimes, we don't even realize a star is a yellow hypergiant until its behavior changes dramatically. Its brightness fluctuates, or it sheds massive shells of gas, revealing its unstable nature. What makes this rarity even more fascinating is that these stars aren't born to be yellow hypergiants. They are massive stars that happen to be passing through this brief evolutionary phase, making them like cosmic travelers pausing only momentarily at a golden-lit crossroads before moving on. This is why finding one feels like discovering a rare photograph of an animal in the wild. You're witnessing something few ever get to see, and it may never appear the same way again. The golden glow of a yellow hypergiant is one of its most striking features. It's the very thing that makes it stand out visually from the colder reds and the blisteringly hot blues scattered across the galaxy. But the question is, why yellow? Why does a star of such massive scale and unstable nature shine in this warm, honey-like hue? The answer lies in the intricate interplay between temperature, chemistry, and the way starlight interacts with matter. Color in stars is essentially a temperature gauge. A star's surface temperature determines what wavelengths of light it emits most strongly, which our eyes interpret as color. Blue stars are extremely hot, with surface temperatures often above 20,000 degrees Celsius, blasting out light at shorter wavelengths. Red stars are cooler, at around 3,000 degrees Celsius, radiating longer wavelengths. Yellow hypergiants, however, sit in between these extremes. Their surface temperatures typically range from about 4,000 to 7,000 degrees Celsius, hotter than red supergiants, cooler than blue supergiants. This temperature range peaks in the visible spectrum, where yellow and white light dominate. But it's not just temperature that gives them their golden character. It's also their immense size and the layers of gases enveloping them. The outer atmosphere of a yellow hypergiant is thick and extended, filled with elements forged in the star's core and dredged up through powerful convection currents. These layers can absorb and scatter certain wavelengths of light, subtly shifting the perceived color. This effect is enhanced when a star is losing mass rapidly, creating a semi-transparent shell of dust and gas that can act like a cosmic filter, tinting the light toward the yellowish end of the spectrum. Another factor is the so-called line blanketing effect in stellar atmospheres. Heavy elements, things like sodium, iron, and calcium, present in the upper layers of the star's atmosphere can absorb specific wavelengths of light, especially in the blue and ultraviolet parts of the spectrum. When those parts of the light are diminished, the balance of color we receive tips toward yellow and gold. This means the color we see isn't just the pure heat radiation. It's been sculpted by the chemistry of the star's outer layers. There's also the dynamic nature of their color to consider. Yellow hypergiants are not stable, so their surface temperature and brightness can fluctuate over time. In some observation periods, a yellow hypergiant may lean more toward a whitish gold when slightly hotter, and at other times when it cools, it can drift into a rich amber shade. This variability can happen over the course of years or even months, which makes observing them a constant game of catching their mood at the right moment. One famous example is Rho Cassiopeiae, a star that has been seen changing its color temperature due to massive outbursts and surface instability. In its hotter phases, Its light appears more whitish gold, while in cooler phases, after shedding large amounts of material, it takes on a deeper, burnished gold. This shifting color is a visible clue to astronomers that the star's outer layers are in chaos, expanding and contracting like the slow breath of a colossal being. It's worth noting that the golden glow of a yellow hypergiant is not as straightforward as pointing a telescope and seeing pure yellow. To the naked eye, even if one were close enough to see it without being blinded, the star might appear as a piercing white with a subtle yellow tint, because our eyes adapt to extreme brightness by washing out saturation. The rich golden imagery we associate with them often comes from filtered and color-calibrated astronomical photography, where the star's spectrum is carefully recorded and rendered to represent its true color balance. However, this golden color is not just a beautiful accident, it's a signal of the star's life stage. It tells astronomers that the star has cooled from its earlier, hotter blue phase, but has not yet plunged into the cooler red supergiant phase. It's like the cosmic equivalent of autumn leaves, brilliantly colored because they're in transition and destined to change again soon. The color is a marker of fleeting stability, a rare moment when a massive star is balanced precariously between two vastly different evolutionary states. The hue also has implications for what's happening deep inside the star. Yellow hypergiants have already burned through much of their core hydrogen fuel, moving on to fusing heavier elements. The change in core energy production alters the balance between the outward push of radiation and the inward pull of gravity, which in turn causes the star's outer layers to expand and cool slightly. That cooling shifts its peak emission away from the intense blue-white of its youth toward the softer yellow-white region of the spectrum. In other words, the golden glow is a visible signature of a star slowing down from a sprint into a stagger, still powerful, but showing the first signs of exhaustion. Even the surrounding space can influence how we perceive their color. Many yellow hypergiants are enshrouded in dust they have thrown off in violent outbursts. This dust can scatter blue light more than red or yellow, much like Earth's atmosphere makes sunsets appear redder. As a result, some yellow hypergiants appear warmer and more golden than they might if seen through a perfectly clear line of sight. This cosmic sunset effect not only enhances their visual beauty, but also provides astronomers with valuable data about the amount and composition of material the star has shed. The golden hue of a yellow hypergiant is more than just a pretty face. It's the product of heat, chemistry, instability, and the star's own turbulent history. It's a glowing testament to the fact that stars are not static points of light, but living, changing entities whose colors tell a story written in the language of physics and time. And for the brief period when a massive star wears this golden crown, it becomes one of the most visually captivating and scientifically intriguing objects in the universe. The story of a yellow hypergiant doesn't begin in a calm, quiet corner of the cosmos. It begins in the most chaotic, crowded, and violent neighborhoods the universe can create, stellar nurseries. These are colossal clouds of gas and dust, stretching for dozens, sometimes hundreds, of light years across, known to astronomers as giant molecular clouds. To the naked eye, they might look like dark patches against a starry sky, but within them, the building blocks of some of the most massive stars ever born are quietly gathering under the relentless pull of gravity. A yellow hypergiant starts its journey much like any other star. A region within the molecular cloud becomes unstable, perhaps triggered by the shockwave from a nearby supernova or the intense stellar winds from an older generation of massive stars. This disturbance causes the gas and dust to begin collapsing inward under its own gravity. But unlike the regions that will give birth to sun-like stars, the part of the cloud destined to form a yellow hypergiant is exceptionally massive, often containing many tens or even hundreds of times the mass of our Sun, all concentrated in one forming star. As the gas collapses, it doesn't fall straight inward like rain into a drain. Instead, it twists and swirls, forming a spinning accretion disk around a growing protostar at the center. Material from the disk spirals inward, crashing onto the newborn star with unimaginable force, heating it to millions of degrees in the core. This early stage is marked by fierce competition. In such a crowded nursery, multiple stars may be forming close together, stealing material from one another, or blasting each other with powerful radiation that halts further growth. But the protostar that will become a yellow hypergiant wins this battle. It gathers an enormous mass before its own intense light begins to push back against the surrounding material. The sheer scale of energy output during this growth phase is staggering. Even before it begins nuclear fusion, the gravitational collapse alone generates enough heat to make it shine brightly in infrared light, visible to telescopes that can peer through the dusty shroud. Once nuclear fusion ignites, hydrogen atoms smashing together to form helium in the core, the star's luminosity explodes. Within just a few million years, a blink compared to the billions our sun will live, it becomes a blistering blue supergiant, radiating energy so powerfully that it begins carving away at its own birth cloud, pushing the gas back and revealing itself to the galaxy. It's important to note that only the most extreme birth environments can produce stars massive enough to one day become yellow hypergiants. In smaller clouds or in quieter stellar nurseries, stars like our Sun are the norm. But in these extreme regions, places like the Carina Nebula, the Tarantula Nebula in the Large Magellanic Cloud, or the Cygnus X star-forming complex, nature operates on a different scale entirely. Here, clusters of massive stars form together, bathing their surroundings in ultraviolet light and shaping the entire region with their stellar winds. This environment is not just physically intense, it's dangerous for young stars. Massive stars pump out radiation so fierce that it can strip away material from their neighbors before they even have a chance to fully form. That means the protostar destined to become a yellow hypergiant must grow fast, accreting huge amounts of mass in a very short time, before the very environment that created it tears it apart. This rapid formation is part of why yellow hypergiants are so rare. It's not just that their later lives are short, but that the exact conditions for their birth are uncommon to begin with. Once the star has accumulated enough mass, often 20, 30, or even more than 40 times the mass of our Sun, it begins its first main sequence phase as a blindingly hot blue star. For most massive stars, this stage would continue for millions of years before they cool and expand into red supergiants. But for some, depending on their mass, metallicity, the abundance of heavy elements, and internal processes, there's a detour. Instead of going straight from blue to red, they pass through the unstable, luminous middle ground that we know as the yellow hypergiant stage. In a way, the entire chaotic birth environment shapes this destiny. A star born in an extreme stellar nursery is already primed for instability. Its massive size means its core burns furiously, and the pressure between gravity pulling in and radiation pushing out is delicate. It's as though the star is born running at full speed, with no intention of pacing itself for a long journey. This furious pace is written into its life story from the moment the first clumps of gas began to gather in that dark cloud. By the time a yellow hypergiant reveals itself to astronomers, most of its birth environment has long been blown away, leaving only faint traces in the form of expanding gas shells or faint nebulae. But if we could rewind time and watch its origins unfold, we'd see one of the most spectacular acts of creation in the universe, a colossal storm of gas collapsing into a blazing giant, forged in a place where the universe itself seems to favor extremes. Yellow hypergiants exist in a precarious and fascinating position within the grand narrative of stellar evolution. They are neither in the cool, expanded comfort of the red supergiant stage, nor in the searing, high-energy realm of the blue supergiant phase. Instead, they occupy an unstable middle ground, a brief transitional state where their physical characteristics fluctuate dramatically as they attempt to balance the competing pressures of gravity pulling inward and radiation pushing outward. This is not a place where stars can linger for long. In cosmic terms, their time here is fleeting, sometimes lasting only a few thousand years, a blink when compared to the millions of years they may spend in other stages. This brevity adds to their rarity and mystery, because the chances of catching a star in this exact state are incredibly slim. The physics of this transition is rooted in the star's struggle to maintain equilibrium. A yellow hypergiant has already burned through much of its hydrogen fuel during its earlier main sequence life. After evolving into a red supergiant and expanding to gargantuan proportions, it finds itself losing stability. The outer layers, bloated and tenuously held by gravity, can no longer be supported effectively. Pulsations, massive stellar winds, and radiation pressure begin driving material away at astonishing rates, sometimes equivalent to losing the mass of the Earth in just a year. This immense mass loss fundamentally changes the star's internal balance, stripping away outer layers and revealing hotter zones beneath. This heating gradually shifts the star's surface temperature upward, nudging it toward the blue side of the spectrum. But the journey is not straightforward. Yellow hypergiants can fluctuate wildly in temperature and luminosity during this phase. Their instability means they can drift toward hotter blue supergiant temperatures, only to reverse course and cool down again, swinging back toward the red supergiant territory. These oscillations are driven by complex interactions between the star's internal nuclear burning layers, convection currents, and envelope structure. In some cases, the instability is so severe that the star's atmosphere swells and contracts dramatically over short time periods, producing visible changes in brightness. Astronomers suspect that this erratic behavior may be linked to the so-called yellow evolutionary void, a theoretical region of the Hertzsprung-Russell diagram where stars cannot remain stable for long. Yellow hypergiants appear to skirt the edge of this void, constantly trying to push through it, but being forced back by the violent consequences of crossing its boundary. As these transitions unfold, the star's chemical composition changes as well. Layers of the star's surface become enriched with heavier elements created by nuclear fusion in its core and dredged up by convection. These include carbon, nitrogen, and oxygen, elements that will eventually be cast into space to enrich future generations of stars and planets. The winds carrying this enriched material are among the strongest seen in the stellar world, leaving behind enormous circumstellar envelopes of gas and dust. These envelopes can obscure the star in visible light, but glow brightly in infrared, providing clues about the star's mass loss history. Observing these shells is like reading the biography of the star's late life, each layer marking a different chapter in its tumultuous decline. The transitional nature of yellow hypergiants is also deeply tied to their fate. The direction in which the star ultimately settles after this phase can determine the type of supernova it will produce. If the star sheds enough mass to become a blue supergiant, it might end its life in a supernova similar to SN 1987A, one of the most studied explosions in modern astronomy. If it instead cools back into a red supergiant, its final explosion may follow the more traditional pattern of a Type 2P supernova. This uncertainty in outcome makes yellow hypergiants especially intriguing to astronomers, as they are living laboratories for studying the late stages of massive star evolution and the conditions that lead to different supernova types. However, because this phase is so short-lived, observing yellow hypergiants in action is a rare privilege. Our galaxy likely contains only a handful at any given time, hidden among billions of other stars. Even when identified, their rapid changes challenge long-term study. Variations in brightness, temperature, and spectrum can occur over mere decades, incredibly fast by stellar standards. This means that astronomers monitoring a yellow hypergiant may witness dramatic changes within their own careers, something almost unheard of for most stars. Each observation adds a piece to the puzzle of how stars transition between giant phases, and why some survive the journey while others plunge into premature catastrophe. The instability during this stage is not merely a side effect. It is the essence of the transitional phase. The star's internal structure is in constant flux as it burns heavier and heavier elements in its core, climbing the nuclear fuel ladder toward iron, the point beyond which fusion can no longer provide outward pressure. This process generates waves of thermal and convective instability that ripple through the star's vast body, creating episodes of expansion and contraction. The surface may experience sudden brightening events, possibly caused by deep-seated convective plumes erupting to the surface and dumping energy into the outer layers. Other times, sudden dimming can occur when thick dust clouds, ejected by recent mass loss events, drift across our line of sight. These cycles can repeat unpredictably, making yellow hypergiants some of the most temperamental objects in the stellar zoo. As the transitional phase continues, the yellow hypergiant is essentially caught in a cosmic identity crisis. Its mass loss is too intense for it to remain a red supergiant, yet it has not yet contracted enough to settle as a stable blue supergiant. The physics driving it forward is relentless. Stellar evolution does not allow for stasis here. The core contracts and heats up, outer layers are cast off, and the spectrum shifts steadily toward higher energy. Eventually, the star's temperature rises enough to cross the yellow boundary for the final time, moving decisively toward the hot, luminous blue supergiant stage. This marks the end of its brief transitional existence, setting the stage for its ultimate and explosive demise. Even though yellow hypergiants may be short-lived, their impact on their cosmic neighborhood is profound. They sculpt their surroundings with powerful stellar winds, enrich the interstellar medium with heavy elements, and create spectacular nebulae that may persist long after the star is gone. For astronomers, they are precious signposts in the evolutionary pathways of massive stars, offering rare snapshots of processes that usually unfold over timescales far longer than human history. Watching a yellow hypergiant is like glimpsing an actor in the seconds between costume changes, a fleeting, in-between moment that reveals both where they have been and where they are going, but one that will vanish almost as soon as it appears. Yellow hypergiants live in a constant state of turmoil, as if the universe itself built them to be restless. Their very structure is a war zone of forces, gravity pulling in, radiation pushing out, and fusion processes surging with erratic energy. Unlike more stable stars that can maintain a balanced rhythm for millions or billions of years, yellow hypergiants are in a perpetual struggle to find equilibrium, and they almost never succeed. Their outer layers are loosely bound, so even small disruptions deep in the core can send ripples through the entire star, ejecting massive amounts of material into space. This instability is not a temporary quirk, it's a defining trait. They are stars on the verge of something catastrophic, always teetering on the edge of change or collapse. The root of this chaos lies in their enormous size and advanced stage of life. Yellow hypergiants are burning through their nuclear fuel at an incredible rate, their cores churning with fusion reactions that alternate between violent surges and sudden lulls. These fluctuations aren't just minor adjustments. They can drastically change the star's brightness, temperature, and size in relatively short periods of time. Astronomers have recorded changes in some yellow hypergiants that happen over just decades, an absurdly fast pace in stellar terms, where many transformations take millions of years. This rapid instability means the star is always shifting, always unpredictable. Inside, the core is a cauldron of extreme pressure and temperature, with fusion processes advancing beyond the simple hydrogen to helium reactions of a younger star. At this stage, heavier elements begin fusing, creating complex energy dynamics that are difficult to maintain in balance. Each new fusion process releases energy differently, and when one layer of the core transitions to burning a new element, the sudden shift can send shock waves through the star. These waves ripple outward, causing the star's vast outer envelope to expand, contract, or even erupt in massive bursts. This is why yellow hypergiants can have such erratic light curves. The flow of energy from the core is anything but steady. Their instability is also tied to their precarious position in stellar evolution. As stars grow in size and complexity, they become more sensitive to small disturbances. In a yellow hypergiant, the outer layers are so distended and tenuous that they're barely held by gravity. This makes them prone to mass loss events, where the star suddenly sheds enormous amounts of material into the surrounding space. These events can happen in pulses, with each one reshaping the star's atmosphere and altering its future path. Over time, such mass loss can strip the star of a significant portion of its outer layers, revealing hotter material underneath and pushing it toward the blue supergiant stage, or possibly toward a dramatic supernova. From an observational perspective, this instability makes yellow hypergiants fascinating but challenging to study. Their surface can undergo dramatic shifts in temperature, sometimes swinging between cooler yellow tones and hotter white or bluish hues. This variability in temperature is tied to the turbulent flows of energy from the core, which can cause the star's photosphere to expand or contract. When the outer layers puff outward, the star cools and reddens slightly. When they collapse inward, the star heats up again. These shifts can happen repeatedly over a relatively short timescale, giving yellow hypergiants a kind of pulsating life cycle, though not as regular or predictable as true pulsating variable stars. One of the most dramatic consequences of their instability is the creation of vast, dense clouds of gas and dust around them. The material ejected from their outer layers doesn't just vanish, it drifts outward, forming a cocoon-like shell around the star. In some cases, these shells can block or scatter the star's light, creating irregular dimming events. In others, they can reflect the star's intense radiation, giving the surrounding nebulae an eerie glow. These ejected layers are a preview of the kind of material that will one day enrich the interstellar medium when the star ends its life, seeding the galaxy with heavy elements forged in its turbulent heart. The energy shifts within a yellow hypergiant are so extreme that even their gravity struggles to keep up. The outer atmosphere is a delicate balance between being pulled in and blasted outward. In some cases, the outward pressure wins decisively, launching stellar winds at speeds of hundreds of kilometers per second. These winds carry away mass at rates far higher than in most other types of stars, further shortening the yellow hypergiant's lifespan. If a star's life is measured by how quickly it burns through its mass, then a yellow hypergiant is a cosmic sprinter, racing toward its end at breakneck speed. All of this violent instability means that yellow hypergiants are essentially living in the shadow of their own destruction. Every pulse, eruption, or mass loss event is a step closer to their final act. This final act could take several forms, depending on their remaining mass and internal conditions. They might evolve into hotter blue supergiants before collapsing in a supernova, or they might shed enough material to become a luminous blue variable first. In some rare cases, their instability could lead to massive eruptions so energetic that they briefly rival the brightness of an entire galaxy, precursor events to their inevitable death. What makes their instability so compelling is that it's not just a sign of weakness or decay, it's also a source of creation. The very turbulence that makes them unstable is what allows them to eject heavy elements into space. These elements, carbon, nitrogen, oxygen, and beyond, are the raw ingredients for new stars, planets, and life. Without the violent, unstable lives of massive stars like yellow hypergiants, the universe would be a far less complex place. In this way, their instability is both destructive and creative, a paradox at the heart of their existence. They are, in essence, stars that cannot stand still. Every moment of their existence is shaped by violent change, by the shifting balance between gravity and energy. They are always on the edge of something: collapse, eruption, transformation. And it is this precarious nature that makes them some of the most fascinating objects in the cosmos. Their instability is not a flaw, but a natural consequence of being so massive, so luminous, and so advanced in their evolution. They burn too brightly, live too large, and change too quickly to ever be calm. And perhaps that is why they are so rare. The universe cannot sustain such extremes for long. Imagine standing on Earth, looking up at the sky on a clear night, seeing our sun as a blindingly bright dot. Now, take that dot and stretch it until it could swallow the orbit of Mercury, then Venus, then Earth itself, and keep going until Mars' path is engulfed. That's the kind of scale we're talking about when it comes to yellow hypergiants. These stars aren't just big, they're unfathomably colossal, the kind of objects that defy normal comprehension. If our sun were the size of a regular basketball, a yellow hypergiant could be the size of a stadium dome, towering over you so completely that the basketball would look laughably insignificant beside it. Think about Earth's diameter, about 12,742 kilometers, and multiply it hundreds or even over 1,000 times. If you were to start driving along the surface of a yellow hypergiant at highway speed, you'd have to keep your foot on the accelerator for months before even making a fraction of a lap around it. To fly around one in a modern jet plane? Forget hours. You'd need decades. And even light itself, the fastest thing in the universe, which can travel around Earth 7 times in a single second, would take a substantial amount of time just to cross the span of such a star's bloated, luminous atmosphere. Picture the International Space Station orbiting our planet every 90 minutes. Now, scale that up. If the ISS tried to orbit a yellow hypergiant at the same relative distance from its surface as it does from Earth, the station's orbital period could be measured not in minutes, but in days or even weeks, because the sheer size of the star would demand an enormous orbital path. Our Sun, impressive as it feels to us, would be utterly lost in comparison. Not just dwarfed, but practically erased when placed against the backdrop of one of these titans. If you could line up suns side by side like marbles, you could fit hundreds, even thousands of them across the diameter of some yellow hypergiants. And if you stacked them in 3 dimensions to fill the entire volume, you'd be talking about millions of suns swallowed effortlessly inside. Imagine an entire star system, multiple planets, moons, and asteroid belts, fitting neatly within the star's boundaries. Now think about Earth's orbit around the Sun. That's 150 million kilometers, 1 astronomical unit. A yellow hypergiant surface could reach close to or even beyond that distance. If such a star replaced our Sun in the center of the solar system, Earth would be scorched and vaporized within its upper atmosphere. Mars could be uncomfortably close to its fiery skin, and Jupiter might find itself basking in a relentless, searing light, far brighter than anything we've ever experienced. To grasp the sheer bulk, consider mass. Some yellow hypergiants can be dozens of times more massive than the Sun, but their immense volume means their density is far lower. They're swollen, airy giants, their outer layers stretched thin by the tremendous heat and radiation pushing outward from within. It's like comparing a dense steel ball to an enormous hot air balloon. The balloon might be vastly bigger, but much of it is empty space. Even so, their presence in the cosmos is anything but light. If one sat where our Sun is now, its glare would be so intense that the night sky would vanish entirely. No stars, no Milky Way, just an all-consuming brilliance flooding every surface. Shadows would be obliterated, and the concept of darkness would be erased. For a more earthbound analogy, imagine climbing the tallest building you know, then stacking another just like it on top, then another, and another, until the stack reached beyond the clouds. That staggering feeling of size still wouldn't come close. Or think about standing at the edge of the Grand Canyon, gazing across the yawning chasm. Now stretch that distance thousands of times over in every direction, and you might begin to sense what it's like to stand in the imagined shadow of a yellow hypergiant. Even their light carries a hint of their magnitude. The photons streaming from their surface began their journey not seconds ago, like the sunlight we know, But after traveling from deep inside for thousands or tens of thousands of years, pushing through the dense stellar matter before finally escaping into space. Once free, they can illuminate worlds across unfathomable distances. And still, when that light reaches us, it's so brilliant it can be spotted with the naked eye from thousands of light years away. If a yellow hypergiant were a campfire, it wouldn't just warm the people sitting around it. It would set the entire forest ablaze. Its influence spreads far beyond its physical boundaries, dominating its galactic neighborhood. Its stellar winds, streams of charged particles, could strip atmospheres from planets light years away, altering the fate of entire systems before those planets even had a chance to form life. And the most staggering part? Even at such an absurd scale, these stars are fragile in cosmic terms. They exist in a precarious state, bloated by their own fusion furnaces to the point of instability. One small shift in their delicate balance between gravity pulling inward and radiation pushing outward, and the whole star could collapse or explode in a supernova that would outshine its host galaxy. That means these giants, as vast and awe-inspiring as they are, live fast and die young. Brief titans in a universe of longer-lived, smaller stars. Trying to truly imagine their size is like trying to imagine infinity. The brain will always fall short. But the attempt alone leaves you with a deep sense of humility. We walk beneath a modest star and already feel small. Beneath a yellow hypergiant, if you could stand at a safe distance and look up, you would feel not just small, but like a speck in an ocean, too vast for the mind to map. It's the kind of scale that forces you to realize the universe doesn't just operate on numbers bigger than we can count. It operates on magnitudes bigger than we can even picture. If you were to drift somewhere in the same galaxy as a yellow hypergiant, the concept of night would take on an entirely different meaning. These stars burn with such intensity that their light is not merely something you see, it is something you feel, almost like a physical presence wrapping itself around you. The sheer luminosity of a yellow hypergiant is staggering, capable of radiating hundreds of thousands, even up to 1,000,000 times the brightness of our sun. Imagine the sun, which already floods our world with life-sustaining light from 150 million kilometers away, multiplied not by 10, not by 100, but by numbers so large that they begin to lose meaning. Even at vast cosmic distances, their glare could pierce through the darkness like a cosmic lighthouse, announcing their presence to any world or wanderer within view. Astronomers often talk about brightness in terms of absolute magnitude, a measurement that compares how luminous a star truly is, without the distortion of distance. On that scale, yellow hypergiants are titans, often far outshining the most familiar giants like Betelgeuse, or even blue supergiants in certain stages of their life cycle. The reason lies in the colossal amounts of energy they churn out every second. Inside their cores, nuclear fusion works overtime, smashing heavier and heavier atoms together, producing not just light, but a relentless flood of photons that blast outward into space. This radiant energy is so powerful that it pushes against the star's own gravity, constantly threatening to rip the star apart. In many ways, their brightness is both their glory and their curse. It's a sign of incredible power, but also a symptom of instability. For any planet unlucky enough to orbit a yellow hypergiant, if such a stable orbit could even exist, the sky would never truly darken. The star's blinding presence would saturate the heavens in a golden white haze, washing out the stars and perhaps even bleaching the landscape in perpetual daylight. Shadows would be sharp and inescapable, etched into the ground like ink marks. From light years away, the star's brilliance could still be strong enough to be visible to the naked eye, making it one of the brightest jewels in a distant sky. For an observer on Earth with a powerful telescope, these stars can appear almost like beacons, their radiance punching through the fog of interstellar dust that would normally dim lesser stars. But brightness in space is more than just an aesthetic spectacle. It's a scientific beacon. That kind of luminosity can act as a cosmic flare, allowing astronomers to spot yellow hypergiants from incredible distances. Their light travels unimpeded for thousands of years before reaching our instruments, carrying with it subtle signatures that tell us about the star's composition, age, and activity. Spectrographs can break that light into rainbows of information, revealing details invisible to the naked eye, like chemical fingerprints etched into the glow. And because they shine so intensely, their light can sometimes illuminate the regions of space around them, acting like a cosmic floodlight that reveals neighboring gas clouds, dust lanes, and even hidden stellar nurseries. Their visibility isn't just a matter of magnitude, it's an emotional presence in the universe. When astronomers peer into the depths of the cosmos and find one of these golden titans blazing in the dark, it's like spotting a campfire in the middle of an endless wilderness. In the same way a lighthouse signals both beauty and danger to sailors, the intense glare of a yellow hypergiant is a signal of extremes. Extreme heat, extreme size, extreme instability. They are, in many ways, celestial performers on borrowed time, putting on the brightest and most dazzling show they can before they collapse into something entirely different. Perhaps a supernova that will shine even brighter for a brief moment, or the formation of a neutron star or black hole. What's remarkable is that even with all that brightness, much of their light doesn't appear to us in the visible spectrum alone. Yellow hypergiants emit a vast range of radiation, from infrared to ultraviolet. Some of that energy is soaked up by surrounding dust and gas, which then re-radiates it in a different form, creating glowing nebulae that can stretch across light years. In effect, a yellow hypergiant's brightness doesn't just end at its surface, it spills into its surroundings, igniting entire regions of space with reflected and scattered light. Astronomers using infrared telescopes can see the warm glow of this dust long after the visible light has dimmed to the human eye. Yet, despite their overwhelming glare, yellow hypergiants aren't always easy to find. That may sound contradictory, but space is full of obstacles. Dust clouds that act like cosmic curtains, gas that absorbs certain wavelengths, and the sheer distances involved mean that even a million suns worth of brightness can be muffled. Still, when the view is clear, these stars dominate their patch of sky. Imagine standing on an alien world 100 light years away, looking up at the night and seeing one star so much brighter than the rest that it casts shadows even during the planet's night cycle. The rest of the stars would appear faint and timid by comparison. Their blinding brightness also hints at something deeper, just how short-lived their existence really is. A star that burns so intensely has to burn through its fuel at a ferocious rate. The light that dazzles us now is a sign of a cosmic sprint, not a marathon. Unlike smaller, steadier stars like our Sun, yellow hypergiants live fast and burn out quickly, their luminosity a flare of life before a violent and inevitable end. And when that end comes, the universe will gain another kind of brightness, the almost unimaginable glare of a supernova, briefly outshining an entire galaxy. In that moment, their story will go from a steady, golden blaze to a single, blinding flash, an exclamation mark at the end of a stellar life. In the cosmic theater, brightness is both allure and warning. Yellow hypergiants command attention, their radiance shouting across unimaginable distances, "I am here and I will not be ignored." They are the kings of their skies, visible even when shrouded, impossible to mistake for anything ordinary. Their light is their signature, their legacy, and their destiny, all wrapped into one incandescent presence that turns the darkness of space into a stage for one of nature's most spectacular performances. Yellow hypergiants are among the most unstable and unpredictable stellar titans in the universe, and nowhere is this instability more evident than in their violent outbursts. These events are not mere flares or momentary hiccups in brightness. They are colossal acts of stellar upheaval, where the star quite literally throws part of itself into space. This process can unfold over days, months, or even years, and when it does, the surrounding cosmic neighborhood is forever altered. The mechanism behind these outbursts lies in the delicate balance, or rather imbalance, between the immense outward pressure of radiation from the star's core and the equally intense pull of its own gravity. For a star as large and luminous as a yellow hypergiant, the forces at play are so extreme that the slightest shift in temperature, opacity, or internal pressure can cause the outer layers to surge outward violently. At their core, these stars are burning through nuclear fuel at a staggering rate, producing unimaginable amounts of energy. This energy radiates outward in the form of photons, but the outer layers of the star, dense with ionized gas, act almost like a semi-transparent wall that traps and releases radiation in an uneven rhythm. When the internal pressure builds beyond a threshold, the star's surface can suddenly expand, causing a pulsation. These pulsations are not gentle oscillations. They are vast heaving motions in which the star swells to a size even greater than its already immense radius. As it expands, the gravity holding the outer layers weakens, and the material at the surface can be pushed past escape velocity. This ejected material is hurled into space, carried away by ferocious stellar winds moving at hundreds of kilometers per second. The amount of matter expelled in a single violent outburst is staggering. In some recorded cases, yellow hypergiants have been observed shedding a mass equivalent to several Earths, or even entire Jupiter masses, into space within relatively short spans of time. Over the course of their unstable phase, a hypergiant can lose several solar masses of material, effectively rewriting its own future. The sheer scale of these events is difficult to comprehend. Imagine a sphere of gas larger than the orbit of Mars being thrown into space, glowing from the heat of its birth and carrying with it the heavy elements forged in the star's interior. This ejected matter can form spectacular nebulae around the star, glowing shells of gas that bear the fingerprints of the violent moments that created them. During these episodes, the star's size can change dramatically. In extreme cases, a yellow hypergiant might expand by several hundred solar radii, becoming temporarily more like a red supergiant before contracting again. This constant swelling and shrinking is a visible manifestation of the instability deep inside. As the outer layers are cast away, the star's surface temperature can fluctuate wildly, sometimes cooling as the surface area increases, then heating rapidly again as the star contracts. To distant observers, this can cause abrupt changes in brightness, leading astronomers to sometimes mistake these eruptions for other phenomena, such as nova events or eruptions from luminous blue variables. The stellar winds that accompany these outbursts are just as important as the pulsations themselves. Yellow hypergiants possess some of the most powerful stellar winds known, driven not only by radiation pressure, but also by the chaotic turbulence of their extended atmospheres. These winds can strip the star of mass at rates millions of times greater than the Sun's solar wind. As the wind carries matter outward, it interacts with earlier ejected shells, creating shock waves that can further heat and illuminate the surrounding material. In some cases, the collisions between these shells generate bursts of radiation across the electromagnetic spectrum, from infrared to X-rays. Astronomers studying these outbursts have noticed that they may occur in cycles, though the cycles are irregular and difficult to predict. A hypergiant might remain relatively calm for decades before suddenly entering a period of heightened instability, ejecting massive quantities of material in rapid succession. Other times, the star might seem to settle into a slower rhythm, releasing smaller amounts of gas more continuously through a dense stellar wind. This unpredictability is part of what makes yellow hypergiants such fascinating and frustrating objects to study. Because they are so rare, astronomers have relatively few examples to monitor, meaning that each violent outburst we witness becomes a crucial piece of the puzzle in understanding how these stars live and die. The ejected material from these outbursts doesn't simply drift away harmlessly into the void. It becomes part of the ongoing story of cosmic recycling. The heavy elements within the gas and dust are seeds for future star systems, planetary bodies, and even life itself. Calcium in our bones, iron in our blood, and silicon in the Earth's crust all owe their existence to ancient stars that exploded or shed their mass long ago. In the case of yellow hypergiants, these violent mass loss events are one of the key ways such materials are returned to the interstellar medium. Every time the star hurls matter into space, it is enriching its galactic environment, setting the stage for new generations of stars. Yet, these events also serve as grim milestones on the hypergiant's road to destruction. With each outburst, the star loses mass that it can never regain. This mass loss can accelerate the star's evolution, pushing it closer to the point where it will no longer be able to sustain fusion in its core. For some, this means a final collapse into a neutron star or black hole, preceded by a catastrophic supernova. For others, the stripping away of their outer layers might transform them into a hotter, more compact blue supergiant or Wolf-Rayet star before their end. In either case, the violent outbursts are both a symptom of the star's instability and a catalyst for its eventual fate. From a purely visual standpoint, these episodes are spectacular. If we could observe a yellow hypergiant up close during one of these events, we would see great arcs and plumes of gas rising from the star's surface, glowing faintly as they cool and drift outward. Over months or years, these structures would expand and merge, forming intricate, glowing shells that shimmer in starlight. Some of these nebulae have been photographed from Earth with telescopes, appearing as faint, ghostly halos around their parent stars. They are beautiful, but also ominous, signs that the star is slowly tearing itself apart. Ultimately, the violent outbursts of yellow hypergiants are more than just dramatic episodes in an already turbulent life. They are the clearest signs that these stars are living on the edge, unable to find stability, and destined for a spectacular end. Every pulse, every gust of stellar wind, every plume of ejected material is both a release of pent-up energy and a step toward an inevitable collapse. And while the timescales may span thousands or even millions of years, each violent outburst is a reminder that even the most massive and powerful objects in the universe are subject to the same truth. Nothing lasts forever, and in the end, even the giants must fall. When a yellow hypergiant sheds its outer layers in one of its dramatic ejection events, that material doesn't just vanish into the cosmic void. It becomes the raw material for some of the most breathtaking structures in the galaxy. The force of the outburst propels vast quantities of gas and dust outward into space at tremendous speeds, spreading in all directions. Over time, these expelled layers form intricate, expanding shells around the parent star. These shells are not merely debris. They are glowing evidence of the star's instability and the incredible forces at play in its atmosphere. The reason these shells can be seen from great distances is that they are not dark, invisible clouds. They shine. This happens because the intense radiation pouring from the central star, still immensely hot and bright despite having lost mass, slams into the expanding material and energizes it. The atoms in the gas absorb this high-energy light and re-emit it at specific wavelengths, producing a visible glow. In some cases, the light is scattered and reflected by the dust grains embedded in the gas, giving the shell a soft, ghostly halo. In other cases, certain elements in the gas, like hydrogen, oxygen, and nitrogen, emit their own distinct colors, creating layered, multicolored nebulae that can stretch for light years across. The shapes of these shells vary, depending on the dynamics of the ejection. Sometimes they are almost perfectly spherical, as if the star exhaled in all directions at once. Other times, they are clumpy, asymmetrical, or even bipolar, with material funneled into two opposing lobes. This variety often comes from complex factors: uneven stellar winds, the star's rotation, localized surface eruptions, and even the gravitational tug of unseen companion stars. If a yellow hypergiant is part of a binary system, the interaction between its ejected material and the companion's gravity can twist the shell into arcs, spirals, or rings. The velocity of these shells is staggering. Even at relatively slow expansion speeds, tens to hundreds of kilometers per second, it only takes a few thousand years for the shell to expand far beyond the original size of the star. But because the surrounding interstellar medium is not entirely empty, these shells can also crash into pockets of existing gas and dust, compressing and shocking them. This interaction not only shapes the outer edges of the nebula, but can also trigger new star formation in the regions it touches. In that way, the death throes of a yellow hypergiant can directly seed the birth of entirely new stellar generations, continuing the cosmic cycle. Astronomers often detect these shell nebulae not just in visible light, but across the electromagnetic spectrum. In infrared, the warm dust glows brightly, revealing the fine structures hidden within. Radio telescopes can detect molecular emissions from the cooler gas in the shells, mapping their density and distribution. Ultraviolet observations, on the other hand, reveal the ionization fronts, the boundaries where intense radiation from the star strips electrons from atoms, producing sharp edges in the nebula's glow. By combining these different wavelengths, scientists can reconstruct a three-dimensional picture of the shell's structure and history, much like examining the rings in a tree to understand its growth. One of the most fascinating things about these shells is how they act as time capsules. The material in each layer represents the physical state of the star at the moment it was expelled. By analyzing the composition of different shells, astronomers can track the star's chemical evolution over time. Early ejections might contain a mix of lighter elements, like hydrogen and helium, while later shells might show heavier elements, carbon, nitrogen, oxygen, produced through nuclear fusion deep within the star's core and dredged up to the surface by convective processes. This chemical fingerprint tells the story of the star's internal transformations, revealing just how unstable and dynamic it has been over its relatively short life. These nebulae are also a signpost for a star's future. Once a yellow hypergiant reaches the stage where it has formed a large, bright shell around itself, it is generally not far, astronomically speaking, from its final collapse. Each mass ejection is both a relief valve and a warning. The relief comes because shedding mass can briefly stabilize the star, lowering the pressure on its core. The warning comes because these events also indicate that the star is running out of options. It cannot shed material forever, and each pulse of instability brings it closer to the point where gravity will win. In the night sky, such shell nebulae are rare sights, partly because yellow hypergiants themselves are rare and short-lived. The shells don't last forever. They expand, fade, and eventually blend into the interstellar medium. Depending on the density of the ejected material and the surrounding space, a shell nebula might remain visible for tens of thousands of years, but eventually its delicate filaments disperse into the galactic background. By that time, the central star may have already undergone its final transformation, collapsing into a neutron star or black hole, with the nebula serving as its only visible memorial. From an artistic perspective, these shells can look like cosmic flowers blooming in slow motion, petals of gas drifting outward in an invisible breeze, lit from within by the star that created them. Some glow in soft yellows and oranges, reflecting their origin in a cooler star's outer layers, while others shine in striking blues and reds from ionized gases. To a human observer, they seem almost impossibly delicate, but they are the result of unimaginably violent stellar events. This combination of beauty and destruction is part of what makes yellow hypergiants such captivating subjects for astronomers and astrophotographers alike. The formation of these nebulae is not just an aesthetic phenomenon, it's also a window into the physics of extreme mass loss. By studying the speed, temperature, and chemical makeup of the shells, scientists can refine models of how massive stars evolve and die. This is important because yellow hypergiants occupy a very narrow and poorly understood phase of stellar evolution, somewhere between red supergiants and blue supergiants, and possibly leading toward luminous blue variables or even Wolf-Rayet stars before the final supernova. Shell nebulae provide hard evidence of the transitions taking place, like snapshots in an otherwise fast-moving film. In some cases, these shells can overlap from multiple ejections, producing a layered, onion-like structure in the surrounding space. Each layer tells of a separate outburst, and together they can record centuries of the star's instability. For the rare few stars where multiple shells are visible, it's possible to watch the legacy of repeated mass loss episodes, each one a chapter in the star's story, spreading outward into eternity. It's worth noting that even after a massive ejection, the material in these shells is still gravitationally bound to the galaxy as a whole, meaning that it will one day mix with other interstellar matter to form new generations of stars and planets. This is one of the quiet ironies of stellar death. Even as a yellow hypergiant tears itself apart, it is also building the raw materials for worlds yet to be born. Among the rare and enigmatic yellow hypergiants, there are a handful that have captivated astronomers for decades, both for their sheer scale and for the unpredictability of their lives. Perhaps the most famous of all is Rho Cassiopeiae, a star so bright that it can be seen with the naked eye despite lying thousands of light years away. Located in the constellation Cassiopeiae, this colossal object is one of the largest known stars in our galaxy, boasting a radius over 450 times that of the Sun. But what truly sets Rho Cassiopeiae apart is not just its size, it is its volatility. Astronomers have documented dramatic changes in its brightness over time, often linked to violent mass ejections in which the star sheds huge amounts of material into space. In the year 2000, observers witnessed one of the most remarkable of these outbursts. The star's temperature dropped by more than 1,000 degrees Kelvin in a matter of months, its surface layers swelling outward and cooling as it expelled an amount of mass equivalent to the entire Sun. The scale of this event was staggering, and yet for Rho Cassiopeiae, it was simply part of its turbulent life cycle. The physics driving such behavior is extreme. In stars like Rho Cassiopeiae, the outer layers are unstable, with convection and pulsations constantly moving material up and down. This constant turbulence makes the star's surface prone to instability, so that when internal pressure builds to a critical point, it can trigger massive expulsions of gas and dust. Each ejection changes the star's appearance and alters its future evolution, as it loses more of its mass and shifts toward different stages of its stellar life. These expulsions also enrich the surrounding interstellar medium with heavier elements, seeding the galaxy with material that will eventually form new stars, planets, and even the building blocks for life. Equally remarkable is HR 5171a, often referred to as one of the largest known stars ever directly measured. Situated in the constellation Centaurus, HR 5171a is a true monster of a star, with a diameter more than 1,300 times that of the Sun. To put that in perspective, if HR 5171a were placed at the center of our solar system, its surface would extend past the orbit of Jupiter. Yet for all its immensity, this star is far from stable. Like Rho Cassiopeiae, it is in an advanced stage of stellar evolution, having expanded beyond the red supergiant phase into the unstable yellow hypergiant state. It also happens to be part of a close binary system, with a smaller companion star orbiting so close that the two share a common envelope of gas. This intimate gravitational dance leads to tidal interactions that distort both stars and cause irregularities in their light output. In fact, HR 5171a's shape is not perfectly spherical. It is stretched and bloated, a sign of the gravitational forces at work between it and its partner. Observations suggest that this unusual binary arrangement may be hastening HR 5171a's demise, as the transfer of mass between the two stars destabilizes them further. The behavior of these stars can often defy expectations. In the case of Rho Cassiopeiae, astronomers have noticed that it can remain relatively stable for years, only to suddenly dim and cool within a few months, a phenomenon believed to be tied to shifts in the balance between gravity pulling inward and radiation pressure pushing outward. HR 571a, on the other hand, shows more gradual changes, but its binary nature introduces complex variables that make predicting its future even more challenging. Both stars are living on the edge, in a precarious balance between forces that could cause them to either shed more mass slowly or explode in spectacular supernovae. Studying these specific stars provides astronomers with rare insights into the processes that govern the end stages of the most massive stars. The outbursts of Rho Cassiopeiae, for instance, have been compared to the great eruption of Eta Carinae, even though Rho Cassiopeiae is in a different phase of stellar evolution. These events hint at underlying mechanisms that may be common among massive stars nearing the end of their lives, such as instabilities in their outer layers or the role of internal convective currents. HR 571a's binary interaction, meanwhile, sheds light on how stellar companions can influence each other's fate, potentially merging to form even more massive stars or accelerating their paths towards supernova explosions. There is also an almost romantic quality to observing these stars, knowing that they are incredibly rare and transient. Yellow hypergiants as a whole are estimated to spend only a few tens of thousands of years in this evolutionary stage, a blink of an eye compared to the millions or billions of years that other stars may live. That means catching a star in this phase is like seeing a lightning flash in slow motion, an ephemeral glimpse of a transformation that will soon give way to something even more dramatic. For Rho Cassiopeiae and HR 571a, their time as yellow hypergiants is drawing to a close, and their next steps may involve contracting into hotter blue supergiants or erupting into catastrophic supernovae that will light up their regions of space. Even for experienced astronomers, the sight of these massive stars inspires awe. Observations across different wavelengths, from visible light to infrared and radio, reveal the shells of gas and dust they have thrown off in previous eruptions, like ripples frozen in time around a central beacon. These shells serve as historical records of the star's violent pasts, allowing scientists to piece together their life stories, much like an archaeologist studying ancient ruins. Each eruption adds a new layer to that record, a new chapter in the brief but spectacular saga of their existence. And beyond their scientific importance, there is a sense of cosmic drama to their lives. Rho Cassiopeiae and HR 571a are like celestial monarchs presiding over their domains, radiating immense power but also showing signs of fragility. Their brilliance comes at a cost. The very forces that make them so luminous are also tearing them apart from within. In time, they will vanish, leaving only remnants behind, perhaps a neutron star, perhaps a black hole, perhaps only an expanding cloud of gas glowing faintly in the starlight of others. For now, however, they remain among the most magnificent spectacles in the universe, their names etched in the annals of stellar astronomy as rare jewels of the cosmos. One of the most powerful tools astronomers have to understand yellow hypergiants, such as Rho Cassiopeiae and HR 571a, is spectroscopy, the study of the light they emit across different wavelengths. Unlike casual stargazing, where stars appear as tiny points of color in the night sky, spectroscopy allows scientists to decode the information hidden within that light, revealing secrets about a star's temperature, composition, movement, and internal turmoil. Every photon emitted by a yellow hypergiant carries a fingerprint of the conditions inside and on the surface of the star, and by carefully analyzing these fingerprints, astronomers can piece together the complex puzzle of these rare celestial objects. When light from a star is spread out into its spectrum, it reveals dark absorption lines and bright emission lines corresponding to specific chemical elements. Each element absorbs or emits light at very precise wavelengths, so by identifying these lines, scientists can determine which elements are present in the star's atmosphere. For yellow hypergiants, this is particularly significant because their atmospheres are often enriched with elements that indicate an advanced stage of stellar evolution. Hydrogen and helium dominate, of course, but heavier elements such as carbon, nitrogen, oxygen, and even some rare isotopes can be detected. The presence of these heavier elements is a clue that the star has already undergone multiple cycles of nuclear fusion in its core, and that convective processes have dredged these materials up to the outer layers. The light spectrum, in essence, becomes a chemical roadmap of the star's life, showing which processes have occurred deep within and providing a window into its internal history. Temperature is another critical piece of information extracted from a star's spectrum. The color of the star, which to the naked eye appears yellow, actually corresponds to a specific surface temperature range, typically between 4,000 and 7,000 Kelvin for yellow hypergiants. However, the detailed shape of the spectrum allows astronomers to measure the temperature much more precisely than simple color alone would suggest. Subtle differences in the strengths of certain absorption lines, especially those associated with metals like iron and calcium, can indicate whether the surface temperature is fluctuating, which is often a sign of instability. These fluctuations are crucial to understanding the star's behavior because they often precede massive outbursts or changes in size, serving as predictive indicators of the star's next dramatic move. Spectral analysis also provides insights into the physical conditions of the star's atmosphere, including turbulence, density, and pressure. In yellow hypergiants, the outer layers are extremely unstable and often in motion due to convection, pulsations, and shock waves. This motion causes spectral lines to broaden and shift, a phenomenon known as Doppler broadening. By measuring the width and displacement of these lines, astronomers can infer the velocities of gases in the stellar atmosphere, sometimes hundreds of kilometers per second. Such measurements are invaluable because they reveal the violent dynamics at work, showing how material moves before, during, and after outbursts. In some cases, the lines split or appear asymmetric, signaling that different parts of the atmosphere are moving in different directions simultaneously, a direct signature of the internal chaos of these massive stars. In addition to analyzing the visible spectrum, astronomers use observations across the electromagnetic spectrum to gain a fuller picture. Ultraviolet light, for example, reveals hotter regions and allows the detection of highly ionized atoms that cannot be observed in visible light. Infrared spectroscopy penetrates the dust shells that often surround yellow hypergiants, revealing cooler material ejected in previous outbursts. By combining data from these multiple wavelengths, scientists can construct detailed models of the star's structure and environment, identifying layers of gas moving at different speeds, temperatures, and densities. Each spectral signature is like a puzzle piece, and together they provide an intricate three-dimensional view of the star's current state and its recent history. Spectroscopy also allows astronomers to study the rhythm of the star's pulsations. By taking repeated measurements over weeks, months, or years, scientists can detect periodic changes in the positions and intensities of spectral lines, which correspond to the star expanding and contracting. These pulsations are not just curiosities, they are physical expressions of the balance between radiation pressure and gravity in the star's outer layers. By tracking them, astronomers can infer the star's internal structure, estimate its mass loss rates, and even predict when it might undergo a larger eruptive event. In this way, the spectrum becomes a diagnostic tool, a window into processes occurring deep within the star that are otherwise invisible. Another intriguing aspect revealed through spectroscopy is the interaction between the star and its surrounding environment. Ejected material from previous outbursts can absorb or emit light at specific wavelengths, imprinting additional lines onto the spectrum. These lines often show different Doppler shifts than the star itself, allowing astronomers to measure the speed and direction of the outflowing material. Observing multiple shells around a yellow hypergiant can reveal a layered history of mass loss, with each layer corresponding to a different eruption. In some cases, these shells can even collide, producing shock-excited emission lines that illuminate the chemical composition and dynamics of the ejected material. Through these observations, the spectral fingerprints of the star are not only a record of the star itself, but also a chronicle of its interactions with the surrounding cosmos. Spectroscopy also plays a key role in identifying the presence of companions in systems like HR 5171a. In close binaries, the gravitational tug of a companion can distort the primary star's shape and influence the motion of its outer layers. This causes additional shifts and variations in the spectral lines, allowing astronomers to detect companions that might be too faint to see directly. In some cases, these interactions can lead to enhanced mass loss or asymmetrical ejections, further complicating the star's evolution. By carefully analyzing the spectral signatures of both stars in the system, scientists can model their mutual influence and understand how binary interactions affect the life and death of yellow hypergiants. Perhaps most importantly, spectroscopy provides evidence of instability and impending transformation. By monitoring changes in the spectrum over time, astronomers can detect signs that a star is entering a particularly volatile phase. Increasing turbulence, widening spectral lines, or sudden changes in chemical abundances can all indicate that the star is approaching a massive outburst or the final stages before supernova. In this sense, the spectrum is both a mirror reflecting the star's current state and a crystal ball, offering glimpses into its near-future behavior. Through these spectral studies, astronomers gain not only a scientific understanding, but also a sense of the dramatic, almost theatrical nature of yellow hypergiants. Every pulsation, every ejection, every shift in the spectrum tells a story of a star pushing against its own limits, teetering on the edge of gravitational collapse while casting off immense amounts of material into space. The spectrum is the language through which the star communicates its life story to us, allowing humanity to witness and record events that occur on scales of energy, mass, and distance that are nearly impossible to comprehend. By decoding the spectral secrets of these rare giants, scientists can track the evolution of massive stars, understand the mechanics of mass loss and pulsation, and even anticipate some of the final, catastrophic events that will end their lives. Each observation adds to a growing archive of knowledge, helping astronomers piece together the complex and turbulent lives of yellow hypergiants. Without spectroscopy, these stars would remain mysterious, their immense power and instability hidden behind their seemingly tranquil yellow glow. With it, they become living laboratories of extreme physics, teaching us about the forces that shape the most massive stars in the universe and the ways in which they influence the galaxies around them. The atmospheres of yellow hypergiants are extraordinary chemical laboratories, providing a window into the complex processes taking place deep within some of the universe's most massive stars. Unlike ordinary stars, whose outer layers may remain relatively pristine for much of their lifetimes, yellow hypergiants reveal a surface composition that has been dramatically altered by nuclear fusion, convective mixing, and episodic mass loss. These chemical signatures are not only fascinating for what they reveal about the star itself, but also for how they influence the surrounding interstellar medium, seeding the galaxy with elements that will form future stars, planets, and potentially life itself. At the most basic level, yellow hypergiants still contain hydrogen and helium, the primary fuels of stellar fusion, but their outer layers also show significant enrichment in heavier elements such as carbon, nitrogen, and oxygen. These elements are the byproducts of hydrogen fusion via the CNO, carbon-nitrogen-oxygen cycle, which dominates energy production in stars more massive than about 1.3 times the mass of the Sun. As the star evolves, convective processes dredge these fusion products from the core toward the surface, revealing that the star is in an advanced evolutionary stage. Observing unusually high ratios of nitrogen to carbon, for example, is a direct indication that the star has undergone substantial internal processing and is moving toward the final stages of its life. Some yellow hypergiants also display the presence of even heavier elements like sodium, magnesium, and aluminum. These elements are generated through more complex nuclear processes, including helium burning and secondary fusion cycles that occur later in the star's life. Their presence in the star's outer layers is a clear signal that these stars are not only old in terms of their evolutionary phase, but also highly dynamic in how they transport material from the core to the surface. Each element carries a story about the conditions under which it was formed, how intense pressures and temperatures in the stellar interior create new atomic species, and how convective mixing brings these elements outward, sometimes combined with explosive ejections that throw them into space. Beyond the typical heavier elements, certain yellow hypergiants have been observed to harbor more exotic chemical signatures, including rare isotopes such as lithium and S-process elements like barium and zirconium. These elements are not normally expected to appear in significant amounts in the atmospheres of massive stars, which makes their presence all the more revealing. Lithium, for instance, is usually destroyed quickly in stellar interiors, so its detection on the surface suggests unusual mixing events or specific nuclear pathways. The S-process elements are produced by slow neutron capture within the core or shells of the star, and their presence in the outer layers indicates that mass loss events or convective dredge-up has exposed these internal processes to external observation. Analyzing these chemical fingerprints requires precise measurements across multiple wavelengths. By comparing absorption and emission lines in the star's spectrum, astronomers can determine not only the abundance of each element, but also the physical conditions under which it exists, such as temperature, ionization state, and velocity. For instance, nitrogen lines in a yellow hypergiant spectrum often appear broader or shifted, reflecting the turbulent motion in the star's outer layers. By studying these patterns, scientists can reconstruct the history of the star's internal fusion, revealing which nuclear processes have dominated at various stages of its life. This level of detail is unparalleled for other types of stars, making yellow hypergiants unique laboratories for stellar physics. The chemical signatures also provide clues to the star's mass loss history. Each eruption or pulsation event often removes surface layers that are enriched with these heavier elements, forming the expanding shells of gas and dust that we can observe as nebulae. By examining the composition of these ejected layers, astronomers can determine how the star's atmosphere has changed over time, which parts of the internal fusion cycle are exposed, and how previous outbursts may have altered the star's evolution. For example, if an ejected shell is unusually rich in nitrogen and helium but depleted in carbon, it suggests that the material came from a layer just above the core that had been processed through the CNO cycle, but had not yet been altered by subsequent helium burning. Each shell becomes a historical record, and the chemistry within it allows astronomers to read the star's autobiography in atomic form. Interestingly, yellow hypergiants often show evidence of partial ionization in their atmospheres, meaning that some atoms have lost electrons while others remain neutral. This partial ionization affects both the star's spectrum and its dynamics, influencing how radiation pressure interacts with the outer layers. It can also create regions of instability, where turbulence and pulsation are more likely to occur. By analyzing the specific ions present and their relative abundances, scientists can map these unstable layers and better understand the triggers for mass ejections. These chemical fingerprints are therefore not just passive indicators of the star's evolutionary stage. They actively influence the physical behavior of the star. Some yellow hypergiants also exhibit unusual ratios of isotopes, such as carbon-12 to carbon-13, which provide a deeper glimpse into the nuclear reactions that have occurred in the star's interior. High concentrations of carbon-13, for instance, indicate advanced CNO cycling, while the presence of oxygen isotopes like oxygen-17 and oxygen-18 point to secondary fusion processes. These isotopic measurements are challenging to obtain because they require high-resolution spectroscopy, often from space-based telescopes or sophisticated ground observatories equipped with adaptive optics. Yet they are invaluable for constructing a detailed picture of how these stars evolve and how their mass loss events contribute enriched material to the galaxy. The chemical makeup of yellow hypergiants also has implications for the future of the material they eject. When a star explodes in a supernova, the elements already present in its outer layers are flung into space at incredible velocities. The nitrogen, carbon, oxygen, and heavier elements contained in the atmosphere become part of the interstellar medium, mixing with primordial hydrogen and helium to seed future star formation. In this way, yellow hypergiants are not just chemical curiosities. They are agents of cosmic alchemy, transforming the simplest elements into complex, life-enabling materials and spreading them across their galaxies. Moreover, studying these chemical signatures allows astronomers to compare yellow hypergiants across different galaxies. While Rho Cassiopeiae and HR 5171a are within the Milky Way, similar stars have been identified in the Large Magellanic Cloud and other nearby galaxies. By analyzing their spectra, scientists can investigate whether yellow hypergiants in other environments exhibit the same enrichment patterns, or whether metallicity, the initial abundance of heavy elements in their host galaxy, affects their evolution. Such comparisons are critical for understanding how massive stars contribute to galactic chemical evolution on a universal scale. In essence, the chemical signatures of yellow hypergiants serve as a cosmic diary, recording both their internal fusion history and their interactions with the surrounding universe. Each element and isotope tells a story of pressure, heat, instability, and explosive release, providing scientists with a detailed narrative of one of the most ephemeral and dramatic phases in the life of a massive star. Through careful study of these chemical fingerprints, we gain insight not only into the lives of these rare giants, but also into the broader processes that govern the evolution of galaxies and the chemical enrichment of the cosmos. Yellow hypergiants, despite their breathtaking luminosity and immense size, are living on borrowed time. Their very nature, a combination of extreme mass, unstable atmospheres, and furious internal fusion, destines them for one of the most dramatic events in the universe, a supernova explosion. Unlike smaller stars, which may quietly fade into white dwarfs over billions of years, yellow hypergiants burn their nuclear fuel at an incredible rate, pushing their cores to the brink of collapse. Their final fate is written in the laws of physics, where gravity, radiation, and the energy released by fusion converge in a spectacularly destructive climax. As yellow hypergiants exhaust the hydrogen and helium in their cores, they begin fusing heavier elements, progressing through carbon, neon, oxygen, and silicon. Each stage occurs more rapidly than the last, with some lasting only months or even days. The core becomes increasingly dense and unstable, eventually forming an iron core. Iron is unique among elements because fusing it consumes energy rather than releasing it. Once the core reaches a critical mass, it can no longer support the immense weight of the star's outer layers, and gravitational collapse begins. This collapse happens incredibly quickly, in a matter of seconds, triggering a catastrophic chain reaction. The core implodes, temperatures and pressures skyrocket, and the outer layers are violently expelled into space in a brilliant supernova explosion. The supernova of a yellow hypergiant is not just an event of light, it is a cosmic recycling process. During the explosion, elements that have been forged over the star's lifetime are scattered across the surrounding interstellar medium. Heavy elements like carbon, oxygen, silicon, and iron are ejected at thousands of kilometers per second, enriching nearby gas clouds and providing the raw material for new generations of stars and planets. In this way, the death of a yellow hypergiant becomes a seed for future cosmic creation, turning destruction into the foundation for renewal. The sheer energy released during the explosion can briefly outshine an entire galaxy, making these events visible across vast distances and even detectable in other galaxies billions of light years away. The remnants of a yellow hypergiant's explosion depend largely on the mass of its core at the moment of collapse. If the core is below a certain threshold, it may stabilize as a neutron star, an incredibly dense object composed almost entirely of neutrons. A neutron star has a radius of only about 10 kilometers, but contains more mass than the Sun, resulting in densities so extreme that a single teaspoon of its material would weigh billions of tons on Earth. The magnetic fields around neutron stars are also immense, and some may spin rapidly, becoming pulsars that emit beams of radiation detectable across interstellar space. In other cases, if the core is massive enough, gravity overpowers all forces and collapses it into a black hole, an object with gravity so strong that not even light can escape. The black hole marks the ultimate endpoint of the star's life, a void that continues to influence the surrounding space through its gravitational pull. Before reaching these final states, yellow hypergiants may exhibit smaller-scale eruptions and instabilities that foreshadow their ultimate demise. Their violent pulsations, mass ejections, and shell-forming events are all precursors to the final supernova, revealing the extraordinary pressures building up in their cores. Observing these warning signs allows astronomers to study the final stages of stellar evolution in unprecedented detail, offering clues about the mechanisms that drive core collapse and the conditions necessary for supernova explosions. Each outburst is both a spectacle and a scientific opportunity, a fleeting window into processes that will soon culminate in one of the universe's most extreme events. Interestingly, the transition from yellow hypergiant to supernova is not always linear. Some yellow hypergiants may briefly revert to a blue supergiant phase, undergoing further changes in temperature and luminosity before the core collapse occurs. These shifts complicate predictions about the timing and nature of the supernova, but they also provide vital insights into the delicate balance of forces in massive stars. Every fluctuation in brightness, temperature, or mass loss contributes to our understanding of how yellow hypergiants approach the end of their lives, highlighting the unpredictable, almost chaotic nature of their existence. From a human perspective, the supernovae of yellow hypergiants are awe-inspiring and humbling. These events release more energy in a few seconds than the Sun will emit over its entire 10 billion-year lifetime. They illuminate their surroundings, outshine neighboring stars, and leave behind remnants that can shape the dynamics of entire star clusters. The elements dispersed during these explosions eventually become part of planets, atmospheres, and even living organisms, linking the life and death of a yellow hypergiant to the very existence of life itself. In this sense, these stars, despite their short and turbulent lives, play a crucial role in the cosmic cycle, transforming matter from one form to another in an endless chain of creation and destruction. The inevitability of their fate adds a poignant dimension to their study. Yellow hypergiants are like cosmic fireworks, brilliant but fleeting, showing us the extremes of physics and the transience of stellar life. Observing a yellow hypergiant in its final stages offers not just scientific knowledge, but also a profound reminder of the impermanence and grandeur of the universe. Each star is a narrative of creation, struggle, and ultimate transformation, a testament to the extraordinary forces that govern the cosmos. Yellow hypergiants are not confined to the Milky Way. Their existence has been confirmed in other galaxies, demonstrating that these rare and unstable giants are a universal phenomenon in the cosmos. Discoveries of yellow hypergiants beyond our own galaxy are both exciting and challenging, offering astronomers a broader perspective on how massive stars evolve under different environmental conditions. Observing them in other galaxies allows scientists to compare stellar evolution in varying metallicity environments, distances, and galactic structures, providing clues about the universality and diversity of these exceptional stars. One of the first extragalactic yellow hypergiants identified was in the Large Magellanic Cloud, LMC, a satellite galaxy of the Milky Way located about 163,000 light-years away. The LMC provides a unique laboratory for studying massive stars because it has a lower overall metallicity than the Milky Way. This means that the initial abundance of heavy elements in stars formed in the LMC is smaller, affecting both the star's evolution and its mass loss mechanisms. Despite these differences, yellow hypergiants in the LMC exhibit many of the same characteristics as their Milky Way counterparts: extreme size, unstable atmospheres, pulsations, and episodic mass ejections. Their spectra show similar chemical enrichment patterns, confirming that these stars go through comparable evolutionary stages, even in a galaxy with a different chemical environment. Among the most notable extragalactic yellow hypergiants is HV 11423, located in the Small Magellanic Cloud. This star has drawn significant attention because it illustrates the dramatic variability typical of yellow hypergiants on a galactic scale beyond the Milky Way. Observations have revealed sudden changes in brightness and temperature, similar to the pulsations and eruptions observed in Rho Cassiopeiae or HR 5171a. Spectroscopic studies indicate that its atmosphere is enriched with nitrogen and other fusion products, confirming that it is in an advanced evolutionary stage. By studying HV 11423, astronomers can test whether the processes driving instability and mass loss are consistent across different galaxies, helping to refine theoretical models of massive stellar evolution. In addition to the Magellanic Clouds, yellow hypergiants have been discovered in more distant galaxies as well. Surveys of nearby spiral and irregular galaxies using advanced telescopes have identified candidate yellow hypergiants based on their extreme luminosity, spectral features, and color. For example, several yellow hypergiants have been observed in M31, the Andromeda Galaxy, and M33, the Triangulum Galaxy. These stars are extremely bright, often outshining tens of thousands of other stars in their local regions, which makes them detectable even at millions of light-years away. Their light curves and spectral features resemble those of Milky Way yellow hypergiants, suggesting that the underlying physics governing their behavior, rapid mass loss, pulsation, and instability, is similar regardless of the galaxy in which they reside. Observing yellow hypergiants in other galaxies also provides crucial data on how massive stars influence their host galaxies. The immense mass loss and eventual supernova explosions of these stars inject energy and enriched material into their galactic environments. By studying extragalactic yellow hypergiants, astronomers can better quantify the contribution of such stars to the chemical evolution of galaxies. For example, the nitrogen and oxygen-rich material expelled by these stars can trigger star formation in nearby clouds, effectively linking the life cycle of a single star to the broader evolution of an entire galaxy. In this way, yellow hypergiants act as cosmic engines, shaping the chemical and dynamic properties of galaxies far beyond our own. Another intriguing aspect of extragalactic yellow hypergiants is the challenge of detection and confirmation. Because they are so rare and often embedded in dense star-forming regions, distinguishing them from other luminous supergiants requires careful observation across multiple wavelengths. Visible light observations can reveal their brightness and color, but infrared and ultraviolet studies are often necessary to penetrate surrounding dust and to confirm the presence of specific chemical signatures indicative of a yellow hypergiant. Spectroscopic measurements provide the final confirmation by showing the enriched atmospheres and evidence of instability that define this class of star. Despite these challenges, the increasing power of telescopes like the Hubble Space Telescope and ground-based observatories with adaptive optics has made it possible to identify and study these rare giants in galaxies far beyond the Milky Way. The discovery of yellow hypergiants in multiple galaxies reinforces the notion that these stars are a natural, albeit rare, consequence of stellar evolution among the most massive stars. Their presence across different galactic environments indicates that the combination of high mass, rapid nuclear fusion, and convective instability can occur under a variety of conditions. It also suggests that while they are fleeting in cosmic terms, yellow hypergiants are a recurring feature in the universe, contributing to chemical enrichment, mass recycling, and the broader processes that shape galactic ecosystems. Studying yellow hypergiants beyond our galaxy also provides perspective on the scale and rarity of these objects. In the Milky Way, only a handful of yellow hypergiants are known, but when astronomers expand their search to neighboring galaxies, the total number of identified yellow hypergiants increases, giving scientists a larger sample to understand statistical properties like average mass, luminosity, lifespan, and frequency of eruptions. By comparing these stars across multiple environments, researchers can determine how factors such as metallicity, galactic age, and star formation history influence the development and instability of yellow hypergiants. These studies not only deepen our understanding of yellow hypergiants themselves, but also illuminate the broader processes that govern stellar evolution on a universal scale. Ultimately, discovering yellow hypergiants in other galaxies highlights both the universality and the ephemeral nature of these stars. They are rare jewels scattered across the cosmos, existing in bursts of brilliance that may last only a few tens of thousands of years, a blink of an eye in cosmic terms. Observing them beyond the Milky Way allows astronomers to witness these fleeting phenomena in diverse contexts, enriching our understanding of the life cycles of the most massive stars and the chemical and dynamical evolution of galaxies throughout the universe. Each extragalactic yellow hypergiant is a reminder that the universe is vast, interconnected, and full of transient but profoundly influential phenomena. Studying yellow hypergiants is one of the most challenging tasks in modern astronomy, and the difficulty stems from a combination of their inherent physical properties and the limitations imposed by the vast distances at which they reside. These stars are extreme in almost every sense. They live fast, burn bright, and are volatile both in their outer atmospheres and in their internal processes. For astronomers attempting to unlock the mysteries of these rare giants, each observation presents a unique set of obstacles, demanding ingenuity, patience, and the use of the most advanced technology available. One of the primary challenges lies in their ephemeral lifespans. Yellow hypergiants exist for a remarkably brief period relative to the overall life of a massive star. After forming from enormous stellar nurseries, they pass quickly through earlier stages, such as blue or red supergiants, before entering the yellow hypergiant phase, which may last only tens of thousands of years. While this may seem long from a human perspective, in cosmic terms, it is incredibly short. This means that at any given time, very few yellow hypergiants are active and visible within a galaxy. Their rarity is compounded by their short-lived nature, making the odds of catching one in a particular evolutionary phase exceedingly low. Astronomers must often monitor large portions of the sky over extended periods to increase the chances of observing these fleeting giants, requiring long-term surveys and precise timing. Another difficulty is their unpredictable behavior. Yellow hypergiants are among the most unstable stars known, prone to sudden and dramatic pulsations, eruptions, and mass ejections. Their luminosity can fluctuate significantly over periods of weeks, months, or years, sometimes doubling or halving in intensity. These changes are not always periodic, meaning that a star may appear relatively calm during one observational campaign, only to erupt violently at another time. Such variability makes it challenging to construct consistent models of their structure and behavior, because the conditions observed at one moment may not accurately represent the star's typical state. Scientists must rely on continuous or repeated observations to understand the range of behaviors and to identify patterns in the instabilities that drive mass loss and atmospheric turbulence. The distances involved present another major hurdle. Even within the Milky Way, yellow hypergiants are scattered across vast regions of the galaxy, often situated thousands or tens of thousands of light-years from Earth. Observing stars at these distances requires extremely sensitive instruments capable of detecting faint light, particularly when the star is embedded in dense clouds of gas and dust. Dust obscuration can absorb and scatter visible light, making the star appear dimmer or altering the apparent color, which complicates the analysis of temperature and chemical composition. To overcome this, astronomers employ infrared and ultraviolet observations, which can penetrate dust more effectively. But these observations require specialized space telescopes or highly advanced ground-based instruments equipped with adaptive optics. Each observational technique provides only part of the picture, meaning that comprehensive studies require integrating data from multiple sources and wavelengths. Furthermore, yellow hypergiants are rarely isolated. Many are found in clusters or associations with other massive stars, which can complicate measurements. The proximity of other luminous stars can contaminate the light received from a target yellow hypergiant, making it difficult to disentangle its unique spectral lines and luminosity. This is particularly problematic in distant galaxies, where individual stars are often unresolved, appearing as bright points of light embedded within crowded star-forming regions. Astronomers must use sophisticated image processing techniques and careful spectroscopic analysis to isolate the contribution of the yellow hypergiant from the surrounding stellar population. The turbulent atmospheres of yellow hypergiants themselves introduce additional observational challenges. Their outer layers are in constant motion, with violent convection, pulsation, and episodic mass loss creating an ever-changing environment. This turbulence broadens spectral lines, shifts them unpredictably, and produces complex emission and absorption features. Interpreting these spectra requires not only high-resolution instruments, but also advanced models of stellar atmospheres that can account for non-uniform motion, shock waves, and varying temperatures. Even small errors in modeling these effects can lead to significant miscalculations of the star's mass, radius, or luminosity, meaning that every observation must be treated with caution and precision. Monitoring yellow hypergiants over time to understand their variability also demands long-term observational campaigns, which are difficult to maintain. Telescope time is limited, and astronomers must compete for access to the world's most powerful instruments. A single night of observation provides only a snapshot of the star's behavior, whereas meaningful studies require repeated measurements over years or even decades. This long-term commitment is essential to capture the timing and magnitude of outbursts, pulsations, and mass ejections, but it requires coordination across multiple observatories and, increasingly, the use of automated survey telescopes capable of tracking changes in brightness across wide fields of view. Another subtle but critical challenge is the calibration of measurements across vast distances. Even when a yellow hypergiant is relatively nearby, interstellar dust, galactic background light, and cosmic expansion can affect how its light is perceived. Astronomers must correct for these factors to determine intrinsic brightness, color, and spectrum accurately. In extragalactic contexts, this becomes even more complex, as redshift and additional interstellar material can alter the apparent properties of the star. The process requires careful modeling and comparison with theoretical predictions, introducing further potential sources of uncertainty. Despite all these challenges, astronomers continue to make progress in studying yellow hypergiants, leveraging advances in technology and methodology. Space telescopes like Hubble and Gaia, along with ground-based instruments equipped with adaptive optics and high-resolution spectrographs, have made it possible to observe these stars in unprecedented detail. Time domain surveys and photometric monitoring programs have provided long-term datasets that reveal patterns of variability, while multi-wavelength observations from infrared, ultraviolet, and even X-ray telescopes help paint a complete picture of their structure and activity. Each new observation pushes the boundaries of what is known, helping scientists gradually overcome the obstacles imposed by rarity, distance, and instability. Ultimately, The challenges of studying yellow hypergiants underscore both their elusiveness and their extraordinary nature. These stars exist on the extreme edges of what is physically possible in stellar evolution. They are massive, unstable, ephemeral, and profoundly influential on their surroundings. Observing and understanding them requires not only technological sophistication, but also persistence, creativity, and patience. Every data point obtained from these stars represents a triumph over the limitations imposed by cosmic scale, instability, and rarity, providing humanity with a glimpse into some of the most intense and dramatic processes in the universe. The difficulty in studying them only amplifies their intrigue, reminding us that these giants are as elusive as they are magnificent, and that their lives, though fleeting, hold critical clues about the life cycle of the most massive stars and the evolution of galaxies across cosmic time. Yellow hypergiants, despite their brief and tumultuous lives, play an outsized role in the cosmic ecosystem. Their immense mass and violent activity make them critical agents in the chemical evolution of galaxies. Throughout their lifetimes, they fuse lighter elements like hydrogen and helium into heavier elements such as carbon, nitrogen, oxygen, and even iron in their cores. These elements are not merely trapped within the star. Through intense stellar winds, pulsations, and eventual supernova explosions, yellow hypergiants eject massive quantities of enriched material into the surrounding interstellar medium. This process effectively seeds their galactic neighborhoods with the building blocks necessary for new stars, planetary systems, and the potential ingredients for life itself. The clouds of gas and dust expelled by yellow hypergiants often form beautiful shell nebulae, glowing with the light of the star and gradually dispersing into the galaxy. Over time, these enriched materials become part of molecular clouds, the nurseries where new stars are born. In this way, each yellow hypergiant becomes both a creator and a destroyer. Its life and death recycle matter, enriching the universe with elements heavier than helium, which are essential for the formation of rocky planets, complex chemistry, and even the molecules that may one day support life. By acting as cosmic alchemists, yellow hypergiants bridge generations of stars. They transform simple elements forged in the Big Bang into the complex atomic structures that make planets, atmospheres, and potentially life itself possible. Their influence extends far beyond their immediate surroundings, shaping the composition and evolution of galaxies. Though fleeting and rare, these giants leave a lasting imprint, ensuring that the next generation of stars is richer, more complex, and capable of sustaining the diverse structures that make the universe so extraordinary. Across the infinite expanse of the universe, yellow hypergiants exist as fleeting monuments to the extremes of cosmic existence, their lives a luminous burst of power, fragility, and fleeting brilliance. Unlike the quiet endurance of smaller stars, these titanic celestial bodies live fast and die young, burning with a brilliance that defies ordinary imagination. They occupy a precarious balance between creation and destruction, between light and collapse, and in doing so, they tell a story that is both intensely physical and deeply poetic, a narrative of energy, impermanence, and transformation writ across the cosmos. From the first flicker of their nuclear fires, yellow hypergiants embody a scale of existence that dwarfs human comprehension. They are born in the densest stellar nurseries, their cores igniting with the fury of fusion processes that churn lighter elements into heavier ones at an astonishing pace. Their immense mass ensures that every second of their life is a struggle against gravity, a push and pull between collapse and explosive energy release. In these early moments, their light begins to shine across the darkness of space, a radiant herald of their extraordinary presence, but also a reminder that such brilliance is never stable for long. Unlike stars like our Sun, which burn steadily for billions of years, yellow hypergiants race toward the inevitable, their lifespan a mere cosmic heartbeat, measured in tens of thousands of years, a blink in comparison to the life of a galaxy. Their brilliance is matched only by their instability. Pulsations ripple through their atmospheres, violent eruptions expel massive shells of gas and dust, and their cores churn with extreme pressures and temperatures that defy simple understanding. Every fluctuation in brightness, every sudden outburst, is a visible manifestation of the immense forces at play within these stars. It is as though the universe itself is performing a symphony of energy, with the yellow hypergiant as both composer and instrument. Observing one is to witness the raw, unbridled power of stellar physics. The fusion of matter, the turbulence of gas, and the shaping of galaxies through processes that scatter enriched material across the cosmic canvas. Each eruption not only marks a moment in the star's life, but also contributes to the ongoing cycle of creation, feeding future generations of stars and planets with the elemental building blocks necessary for complexity and life. The poetry of yellow hypergiants is not limited to their physical power. There is an aesthetic, almost mystical quality to their fleeting existence. Their golden glow, which arises from a delicate balance of temperature, composition, and radiative processes, illuminates the surrounding interstellar medium, creating a halo of light and energy that can extend for millions of kilometers. Shell nebulae form around them, clouds of material sculpted by wind, gravity, and radiation, glowing like ephemeral works of art in the vast darkness of space. To contemplate these structures is to sense the transient beauty of forces that are otherwise invisible, massive, chaotic, yet exquisitely ordered in the dance of matter and energy. Beyond their physical and aesthetic impact, yellow hypergiants carry a profound symbolic weight in the story of the cosmos. Their lives are a reminder that nothing, no matter how vast or luminous, is permanent. Even the mightiest structures in the universe are subject to the laws of physics, to the inevitability of change and collapse. They show us that impermanence does not diminish significance. Rather, it can heighten it, for the brief moments of extreme brilliance leave an imprint that outlasts the star itself. The elements they scatter into space will seed nebulae, form planets, and become part of new stars, and in some cases may even form the chemical foundations for life. In this way, the ephemeral lives of yellow hypergiants ripple outward, connecting the death of one star to the creation of countless others, a chain of transformation that stretches across time and space. The supernova explosions that end their lives are the ultimate expression of their transient majesty. In a matter of seconds, these stars release more energy than our Sun will emit over its entire 10 billion-year lifetime, an unimaginable display of power that outshines entire regions of their host galaxies. The remnants, neutron stars or black holes, become enduring markers of what once existed, tiny cosmic tombstones signaling the passing of a giant. And yet, even in death, they continue to influence their surroundings, altering the gravitational landscape, enriching the interstellar medium, and influencing the birth of new stars. Their legacy is both material and symbolic, a testament to the idea that even the briefest of lives can have lasting cosmic significance. Observing a yellow hypergiant, whether in our Milky Way or in a distant galaxy, evokes a mixture of awe, humility, and philosophical reflection. These stars operate on scales of mass, energy, and time that dwarf human experience, yet they communicate universal truths: that existence is fleeting, that power and beauty can coexist with instability and chaos, and that even the briefest flashes of brilliance can leave an indelible mark on the universe. Their lives are an exquisite reminder that the cosmos is not static, but alive with motion, transformation, and cycles of creation and destruction. Every flicker of light from a yellow hypergiant is a heartbeat of the universe itself, a pulse of energy that reminds us that life, in all its forms, is transient yet meaningful. In the end, the story of yellow hypergiants is a meditation on both magnitude and impermanence. They are cosmic fireworks, brilliant, volatile, and fleeting, illuminating the night sky with golden splendor before vanishing in cataclysmic finales. Their brief lives and spectacular deaths encapsulate the extremes of stellar physics while reminding us of the beauty inherent in transience. They seed the cosmos with the elements of life, sculpt galaxies with their energy, and inspire awe with their radiant presence. In contemplating yellow hypergiants, we are invited to witness the grandeur of the universe on both an intimate and cosmic scale, to feel the pulse of creation, the inevitability of change, and the profound, fleeting beauty of existence itself. They teach that even the shortest lives can burn with extraordinary brilliance, leaving echoes that reverberate across space and time, a testament to the extraordinary potential of matter, energy, and the forces that govern the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.